Okay, so 10.4 notes is the integral test for convergence. It says the integral test for convergence states if f is positive, continuous, and decreasing function for x greater than or equal to k, and a sub n is equal to f of x, then the following is true. So we have the summation of n equals k to infinity of a sub n, and the integral of k to infinity of f of x dx. Okay, so both of these things would be true. If one of them converges, the other is going to converge. Okay, if one of them diverges, the other is going to diverge. So we're going to write that both converge or both diverge. Okay, it's very important that you underline or highlight positive, continuous, and decreasing. It has to be all three of those. So before you start any of the integral tests for convergence, your very first step is to make sure that your function is positive. Okay, make sure it's continuous and make sure it's decreasing. If any of those conditions are not met, you cannot use this test. Okay, so you'd have to go and use a different method. Another important thing is in this case, when we're talking about a sub n, we are going to say that that is the same as f of x. Before we look at some examples, I know we typically don't look at proofs, but this is a very important proof. Okay, so we are going to go through this proof. Very important, as in FRQ important. So if you can understand this proof, which means you understand the method, okay, any FRQ that's relating to the integral test for convergence should be easy for you to solve. Okay, so if you understand the proof, and that's our goal here before we look at the examples. So let's start off and look at this graph here. So first off, looking at this, we see that this is a positive function. Okay, so that line. Okay, it's continuous and it's decreasing. Okay, so it checks all three boxes. Now I am going to go ahead and plot the point of the rectangle that touches our graph. So for every single time. Okay, notice you're not going to put a point on the very last one because the corner of one of those rectangles does not touch our line. So this one right here. Okay. Then I'm going to start labeling these A1, A2, all the way to A sub n. So I'm going to say this is A1, A2. I'm going to use some dots to represent that I'm talking about this in an infinite matter. And this is going to be A sub n. And just make sure we denote it as a capital N as not to confuse it with a lowercase n. Okay. Also remember that A sub n is representing f of x. So that means this is the same as saying f of 1, f of 2, and f of n. Okay, we could also label the x-axis down here. Okay, 1, 2, dot, 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 n plus 1. Okay, so once we label all this, what we're going to do is we are going to create the summation. And by summation, remember when we did Riemann sum, it's talking about the areas of all those rectangles added together. Okay, so that's what we're going to do first. So that is going to be the summation of n equals 1 to capital N. Okay, the reason for that is because it's starting right here at 1, and the last point where it touches the graph is at that capital N. Okay, of A sub n. And then now I'm going to look at the integral. Okay, so that's the summation of all the rectangles. Now the integral, which is the area under the curve. Okay, that is going to be from 1 to n plus 1, so those are the bounds. of f of x dx. So now we have to correlate these two things in some way. We have the summation and we have the integral. So looking at all these rectangles, remember when we did Riemann sum, we talked about an over and under approximation. So based off of this Riemann sum, would this be over or under? Over. How do we know? Good. We have a lot of the part of the rectangles that are above our area. So all of this is representing a over approximation, which means if we were to solve both of these areas, which one would be more, the summation or the integral? The summation, so it's greater than or equal to. So we just formed one equation here. Okay. We're going to do the same thing on the other graph. Okay, so I'm going to label the x-axis first. So I have 1, 2, n plus 1. Okay, notice this time when I label the part of the rectangle that's touching the curve, I am not starting at a sub 1. I'm now starting at a sub 2. So I have a sub 2, which is f of 2. Okay, and then I'm going to have a sub n, which is f of n. Oops. And then I have a sub n plus 1, which is f of n plus 1. Okay. Which means I do the same thing. I'm going to do the summation, which is adding all the areas of the rectangles together. So I have from n equals 2. Okay, again, we are starting at n equals 2 because that is the first part of the first rectangle of the corner that touches the curve. Okay, all the way to n plus 1 of an. And then we do the integral, the area under the curve, which is going to be from 1 to n plus 1. Because remember, when we're talking about area under the curve, we're talking about this entire space here, which starts at 1. Okay, and then f of x dx. And then in order to decide what inequality goes between them, we have to look at this Riemann sum and we have to ask ourselves, is this an over or under approximation? An under approximation. Okay, because we have all this space that they're forgetting about. Okay, so this is under approximation, which means the summation of all those rectangles are going to be what in comparison to the integral? Okay, less than or equal to. Okay. So the next part that we're going to do for this proof, so what we did so far is we looked at both an over approximation and an under approximation. The only difference is on the under approximation, it did not start at 1 like the other one. So since it did not start on 1, and we ultimately want all these equations to be some resemblance of each other, so equal to each other. That means that the second graph that we did, we have to add a sub 1. So I'm just going to make a little note of that I'm going to add a sub 1 to both sides. Okay. And again, I'm only looking right here. When I do that, that means this n equals 2 is now going to be n equals 1. I'm now starting at 1. Okay. And my function, f of x dx, is just going to have an added constant at the end, and that constant is plus a sub 1. So I have the summation of n equals 1 to n plus 1 of an is less than or equal to the summation, or sorry, the integral of 1 n plus 1 f of x plus a1 dx. Okay, I added a1 to both sides. Okay, again, I did that because I want this to match up with my very first graph where it started at n equals 1. Okay, now the next thing I'm going to do is I am going to take all of these capital N's and I'm going to look at them as they approach infinity. So as capital N approaches infinity, okay, what's going to happen is every single capital N that I see, so right here, 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 and here, are all going to turn to infinity. No matter if it's n or n plus 1, because plus 1 is insignificant to infinity. Okay, so I'm going to have the integral from 1 to infinity of f of x dx. Okay, that's coming from this part right here. Okay, and remember, this is less than the summation, so that's why I wrote it first. Oops. Okay, then I'm going to do less than or equal to the summation of n equals 1 to infinity of a sub n. Okay, notice when I change them, this and this summation are now the same. Okay, and that is going to be less than or equal to the integral of 1 to infinity f of x plus some constant a1 dx. So this line in the proof is the most important. This is saying that no matter if we're looking at an over or under estimation, no matter what, the summation, okay, of all those rectangles are still going to be between the two integrals, which means if any of the integrals are converging, then the summation has to converge. If the two integrals are diverging, then the summation has to diverge. And that's what just proved the integral test. So any questions on the proof? Okay, out of the whole proof, again, this line is the most important. As long as you can see the connection that the summation is between the two integrals, and that if the integrals are converging, the summation must converge, and vice versa.
Wait, what was the first part of that you said?
First part of what, sorry?
So you said something like the integral.
Oh, if the two integrals converge, then the summation has to converge because it's in between the two integrals.
Wait, what did you say before that part?
I really don't know what I said before that. It's okay. It's all recorded. You can go back and watch it.
Okay, yeah.
Right. Okay. So now let's look at some examples. They only gave us 2 examples for this. So on the first example, we have the summation of n equals 2 to infinity of 1 over n times the natural log of n. Remember, our very first step is to double check if this function is positive, continuous, and decreases. So it's either you know what the function looks like at the top of your head, okay, or you go onto Desmos, which you would have access to. You graph the function 1 over n times natural log of n. And what you'll notice is it kind of looks like the function that's on the proof above. Okay, so it is positive, continuous, and decreasing. So it does fit all 3 of these. Remember, these all have to be true or you can't do the test. If one of them is false, that means you would have to think of a different method to determine if it's converging or diverging. Okay. So we check these all off, and remember, we can graph on Desmos if we don't know. And then the goal for this is to take the limit as some value approaches infinity. So really, we're looking as n approaches infinity, but we don't want to confuse it with the n that's inside of the summation. So what we say is the limit as b approaches infinity. So we're going to let b be that value because we're going to take this summation and we're going to convert it to an integral. Okay, so we are actually looking at the integral from 2 to b. So notice this 2 came from here, the n equals 2, and we're going to infinity, which we said is b. So we just write 2 to b. And then I write out the entire thing, 1 over n natural log of n, and then dn, because we're looking at an integral. Okay, so I convert that summation to the limit of this integral. Then I need to just integrate. Okay, so in order to integrate, you'd have to use u substitution. And what am I going to let u equal? Just the natural log of n, because what's the derivative of the natural log? 1 over x, right, or 1 over n, which eventually will cancel out that extra n. Okay, so we're going to let u equal natural log of n, which means du is equal to 1 over n dn. And then to get dn by itself, we multiply both sides by n. So dn is equal to n du. Okay, so plugging it all in, we have the limit as b approaches infinity of the integral from 2 to b of 1 over nu n du. Okay, we did that because we wanted those n's to end up canceling, so we only have everything in terms of u. Okay, I heard some say we'll let u equal n. Well, the derivative of n is 1, so that it wouldn't really help us. And if we let u equal n natural log of n, that would be using the product rule, which means we would still have some value n in our problem. Okay. So really, I just now have 1 over u du. And so if I was to integrate that, that would be the limit as b approaches infinity of natural log of absolute value of u. But since u is natural log of n, this is natural log absolute value natural log of n, solved at 2 to b. Okay, I plug in b first, and so I have, and I'm gonna go up here so I have more space. Okay, I have the limit as b approaches infinity of the natural log of b minus the natural log of 2. Okay, because I'm plugging in my bounds, 2 and b. And then now looking at this, I can see as b approaches infinity, this entire function here is also going to approach infinity. So really, I have infinity, so this is equal to infinity, plus some number, because the natural log of 2 is just a number. So plus a number, okay, which is insignificant. And I can just say that this is infinity. And since this whole limit is approaching infinity, is this going to converge or diverge? Diverge. Okay, remember, if it approaches infinity, it's diverging. If it approaches 1, it's converging. Okay, so really this is the only new thing that we learned in this section. The rest is, do you remember how to integrate? Do you know your rules of integration? Okay, any questions on 1? Okay, last one, number 2. Okay, same thing. We still have to check if it's positive, which it is, continuous, which it is, and decreases. Again, all true. If you cannot visualize 1 over n squared, then you go to Desmos, you graph it on Desmos, and then you confirm those 3 things, those 3 conditions that way. Okay. So for this, we're going to do the same thing. We're converting this into the limit of an integral. So we say the limit as b approaches infinity. Always b, because we don't want to confuse it with n that's in the summation. Okay. Of the integral from, what's going to be my bounds? 1 to b, okay, of the function. And what's another way I can write 1 over n squared? N to the negative 2, good, dn. So I just set up my integral. From here I integrate, so I have the limit as b approaches infinity of integrating, I add 1, divide by that new exponent. So adding 1 would be negative 1, dividing by negative 1. So this would be minus 1 over n, solved at 1 to b. Okay, or you could have wrote that as negative n to the negative 1, same thing. Then I'm going to solve it from 1 to b. So this is the limit as b approaches infinity of negative 1 over b minus negative 1 over 1. Okay, I'm then going to plug in that infinity. So if I have 1 over infinity, that means that section is approaching 0. So this is equal to 0. Okay, minus a negative turns into positive. So this is plus 1, which means that this limit is approaching 1, so that the series is converges or converging.